So, welcome again to the new lecture of the course Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we have been doing until last lecture. So, in the last lecture we finished on thermodynamics of these materials, basically looking into how these properties are related to each other. So, to begin with, we wrote this thermodynamic expression, we calculated the free energy change, that is minus of S dt minus of Xij d of capital Xij. So, this is strain, this is strain, this is stress. You can also write it as sigma ij if you like, and you can also write small x as epsilon, but we did not use epsilon because epsilon we are using for dielectric permittivity, and then you write this as minus di d of Ei, where this is your you can say charge density, or you can say polarization, and E is the electric field. So, from this we determined what are the properties such as entropy, that was equal to minus of del T x comma E, Xij was equal to minus of del G by del Xij at constant electric field and temperature, and then we also determined what is Di, or you can also say Pi as minus of del G by del Ei at constant temperature and constant stress. From these we determined various. So, if you write the full form of these total differential forms, you can see that entropies, for example, consists of terms such as heat capacity, piezo-caloric effect and electrocaloric effect, whereas if you write the same expression, for example, for the strain, you can see that it consists of terms like thermal expansion, piezoelectric effect, and that is converse piezoelectric effect, as well as compliance, elastic compliance. And if you write the same expression for things like for polarization, you can see it consists of terms because of temperature, that is pyroelectricity, and then because of stress, that is direct piezoelectricity, and then because of change in electric field, that is the dielectric permittivity. And you can combine these together and look at the equivalence of various parameters, such as you can establish equivalence between direct and indirect piezoelectric effect. Thermodynamically speaking, both are similar, right. Similarly, if you establish equivalence between piezo-caloric effect, piezo-caloric connects mechanical to temperature, right. So, it is equivalent to thermal expansion, that is also related to expansion with respect to temperature. So, these sort of properties are interrelated to each other, and then we wrote the constitutive equations for piezoelectricity. So, this sort of provides a little bit of mathematical and thermodynamic basis for writing these expressions. In reality, we use much simpler forms because of symmetry and thermodynamic arguments, and for polycrystalline materials we can take them to be scalar or isotropic. As a result, many of the properties become simplified in polycrystalline materials, but nevertheless it is important from the sake of complete understanding to understand the exact forms of these properties. So, now what we will do is that we will begin in this lecture with our discussion on ferroelectric materials. So, we have looked at the equations related to piezoelectrics, and we have also looked at what piezoelectric phenomena is, and now we will look at the phenomena related to ferroelectric materials. So, ferroelectric materials, let us just go into a bit of history of it. Ferroelectric materials, ferroelectric effect was first seen in. So, we know that ferroelectricity from the basics, if you remember, every ferroelectric is by default a pyroelectric and a piezoelectric, and many of the pyroelectrics and piezoelectrics that we use in practical applications, they are nothing but ferroelectrics. So, ferroelectric effect was first discovered in 1921 by Roger Walasek. He was a Czech scientist, and he discovered this in Rochelle salt, which is nothing but Kna C4H4O6.4H2O. So, it's basically a potassium sodium based salt that shows ferroelectricity. Now, it did not have much research earlier on, but later on after the after the Second World War, there was a renewed interest in these materials, and especially Russians and East Europeans carried out a lot of work on these materials. A lot of work was carried out in US as well, and Walasek, sorry. And so as a result, there are renewed interest. There was a renewed interest in ferroelectrics after Second World War, and a lot of discoveries were made, a lot of devices were made. So it became really popular after the development of vacuum technologies, because one could make thin film of these materials, and these thin films were far more exciting as compared to bulk materials. For example, for ferroelectric memories and data storage devices, they were very potential, they were very important candidates or very interesting candidates upon a time in 90s and 2000s. So a lot of work was done. So development of vacuum techniques led to a lot of thin film work. So ferroelectrics, typical ferroelectrics are, you can say, Rochelle salt. Other than that, you have barium titanate, you have lead titanate, you have PVDF, then we have PVZR TiO3, and then we have SR Ba2 Ta2O9, which is basically a Aureolus kind of compound. Then we have bismuth titanate. Now we have compounds such as BiFe3O3, they are all ferroelectric materials. So there is a huge variety of materials which are ferroelectrics. So for example, they can be divided into certain categories. You can have sulfates, various sulfates which are ferroelectrics. So you can say sulfates. Then we have niobates. Then we have titanates, and titanates and niobates, many of them form to be perovskites, and then we have many of the complex oxides based on perovskite units. So things like bismuth titanate and strontium bismuth tantalate, they are all based on series of perovskites stacked together along a certain axis. And then of course, as I said, Rochelle salt, parent compound and its compounds, related compounds. And then so you have sulfates, niobates, complex oxides, titanates, etc. There are huge series of materials. So if you really wanted to know about the materials, I would recommend you to go through a book, Ferroelectric Crystals by Jonah and Shiran. These two gentlemen are pioneers of ferroelectrics, and they have written this beautiful book, Ferroelectric Crystals. It's a book which goes through a variety of materials and gives you a good insight into ferroelectricity in different materials, their structures, their properties, and so on and so forth. And also it treats with a bit of thermodynamics of ferroelectric materials. Now ferroelectric materials, so we'll see what ferroelectric material is. A ferroelectric materials by nature, it's a nonlinear dielectric. When you switch a ferroelectric under electric field, a ferroelectric shows a hysteresis curve like this. So just like a magnetic material, a ferromagnetic material, the ferroelectric material also exhibits what we call as a hysteresis. So this is polarization, which is in typically Coulomb per meter square, and then voltage or electric field. Okay. So this could be in volt, this could be in volt per centimeter or volt per meter. So what it shows is a hysteresis loop. So essentially at zero field, you have two states which are plus and minus. So we call it plus PR and minus PR. PR is called as remanent polarization, and then this remanent polarization saturates to a polarization which is called as plus PS, and here you will have, so this is plus PR, minus PR, this is minus PS. So PS is called as saturation polarization, and then polarization is 0 not at the 0 field but at a non-zero field which is called as plus EC and minus EC, where EC is called as coercive field. And so basically what happens is, for a ferroelectric, for a virgin ferroelectric, you start in this fashion, and then when you keep repeating the loop, it just keeps making the loop again and again and again and again. You do it for many cycles, it will reproduce the same loop again and again. So this is basically because of as we will see later on, formation of domains in these materials. So the switching process is somewhat similar to what we see in ferromagnetic materials. So in some sense you can call it as a electrical analog of a magnetic material. Okay. In ferromagnetic material, this loop will exist between magnetic field and induced moment or flux density, whereas in this case this is a loop between voltage or electric field versus polarization. So it is, polarization is charge density and this is the electric field. So basically you are measuring the charge density on a capacitor, and this is what you see. The area under the curve is essentially the energy, the product of P and E, which is the product of P and E is nothing but mu divided by V into E, and this is nothing but the energy density. So the energy that is spent in the process of switching. So we will see these mechanisms of why this happened, but this is a typical, you can say, PE, or as we say, hysteresis curve for a ferroelectric. So if a material is ferroelectric, a material will show a non-zero polarization at 0 field, and the polarization is 0 at some finite field, and this is a stable effect. So most important thing is, this is a stable effect, it remains stable for long time. So there is another class of materials called as electrate, in which this phenomena is transient, it is a temporary phenomena. So you will see in electrates also similar sort of loop, but that is not stable as a function of time. So do not confuse, ferroelectric is not a electrate, is not an electrate. So a lot of electrates also tend to show similar loops, maybe of not of very good quality loops, but they show a hysteresis between polarization and electric field, but that is not a permanent behavior. This is a permanent behavior, okay, as long as your temperature is below a certain temperature. So what are the characteristics of a ferroelectric? Ferroelectric material is, one, it is non-centrosymmetric, two, it is polar, secondly, P is reversible upon reversing the electric field. These are must have requirements. And additionally, ferroelectric material shows a transition at a temperature called as Tc, which is called as Curie temperature, above which when you heat it, it becomes paraelectric. So ferroelectric will become paraelectric upon heating at Tc, okay, and there it shows a phase transition. So generally this transition will be from or non-centrosymmetric to a centrosymmetric. So you can see the terms are similar, just like in magnetism we have paramagnetic, we have paraelectric here, just like we have ferromagnetic, we have ferroelectric here. So there is a transition from a non-centrosymmetric phase to a centrosymmetric phase at a temperature Tc, and this Tc is called as Curie temperature. And then in physics language we also call it there is a mode softening at Tc. And the soft mode vanishes at Tc. That is in terms of when you do Raman measurement on these materials, you will see a disappearance of the soft mode at Tc, and this is a signature of ferroelectric and vanishing of soft mode at Tc. Okay. These are certain characteristics of ferroelectric material. So, essentially what happens, so if you take a model example of let us say PbTiO3, okay. PbTiO3 has a perovskite structure. If you draw the structure of PbTiO3, okay, this is the PbTiO3, which is these are all Pb ions. Let us draw the oxygen ions. These are oxygen ions, and then we have somewhere in between we have a titanium ion. This is cubic PbTiO3 with P being equal to 0. This is a centrosymmetric material, it does not have a polarization, it has A is equal to B is equal to C. As you cool it below Tc, so when T is lower than Tc, so this is at T greater than Tc. As you cool it below Tc, this will transform into a tetragonal structure. So, what will happen is that this AB parameters will be different now. So, it will be slightly there will be a lattice distortion leading to the formation of a tetragonal structure where, so this will become tetragonal, where A is B equal to B is not equal to C, and this is P is not equal to 0. So, in this case what will happen is that you have similar atoms sitting at various positions. This is oxygen, do not worry about the sizes, and this will be titanium. Now, the titanium in this case will be slightly off centered. So, this is the central position, right? Titanium will either be here or it will be here. So, this is the downward or upward movement of titanium. So, titanium is little bit shifted with respect to the dipole, with respect to the so you can see that oxygen here makes an octahedra. This is oxygen octahedra, right? And when, so oxygen octahedra will have certain charge, it will have net charge of -4. Titanium has +4 charge. So, let us say if you do a dipole moment calculation, when the center of negative charge and center of positive charge, when they match with each other, when it is in cubic form, so these pluses and minuses match each other, as a result mu is equal to 0. So, this is for this case. Now, when you cool it below, see the central titanium atoms move up or down, as a result now the center of negative charge is somewhere here, this is my negative, and the positive charge is either here or here. So, let us say I take one of them, I take this one, there is a distance delta, let us say delta is in few picometers. Now, what we have is we have a dipole moment of 4 electrons multiplied by delta. So, this is a non-zero dipole moment that is developed, and as a result you have a permanent dipole moment which is called as, and that is why ferroelectric materials show a non-zero dipole moment of polarization at room temperature in the absence of electric field, because they have a non-zero dipole moment. So, these are polar non-centrosymmetric phases which form, and this is manifested in what we call as free energy. So, when you plot the free energy of such a solid. So, let us say when we take free energy as a function of distance or position of atom, let us say position of central atom. Okay. Now, when it is above Tc, then free energy shows a minima. This is at x is equal to 0. X is equal to 0 means center. So, the titanium atom sits right here. However, so this is at T less than greater than T greater than Tc. When the temperature changes, then what happens is that the free energy shows a double well kind of structure. So, there are two minimum positions, these correspond to plus x or minus x, they correspond to minus Pr or plus Pr. So, these are both equivalent energy position. So, this is the maxima now. So, x is equal to 0, you can see there is a local maxima. So, which means x is equal to 0 is not a stable position, atom cannot sit here, atom has to fall either here or here. Okay. So, depending upon the local perturbations, it will either fall into right one or left one. So, as a result, you have two states, one of the two states which is stable as plus Pr or minus Pr, and this is because the titanium atom now sits either here or it sits here. Now, this is what happens in terms of free energy. We will do the free energy discussion a little bit in detail. So, this is basically, you can see this energy is delta E, and this energy, when you do the switching, for example, when you go from plus to minus Pr, you are saying you need to overcome this energy. So, if you look at the hysteresis, for instance, here, now try to relate this to hysteresis. If this is your hysteresis curve, okay. So, this is P E. So, you are at this state plus Pr. At the switching, you have to go. So, when you switch it completely, sorry, the loop is not very symmetric. Let me just make it symmetric. Yeah. So, this is minus Pr and this is plus Pr. So, this is 0. So, as you switch it, so you go from 0 field to here. So, you go from 0 field to here. Let us say this is A, you come to B, then you come to C, then you come to D, you come to E, and you go to F, and then this whole cycle continues. So, as you switch it, you go from 0 to A for a new material, from A you go to B, from B you go to C, you need to apply an extra field to bring it back to 0 polarization, then you go to D, then you go to E again. So, what is happening in terms of energetics? Let us say at B you were in this position. So, let us say this was B. So, for a given region, for it to come from plus Pr to minus Pr, the atom must shift from B to E. So, this position will correspond to E position. So, looking at the free energy diagram, what you see is that as you go from B to E, you need to overcome an energy barrier of delta E, and this delta E is nothing but what we call a switching energy barrier, a switching barrier. So, basically how the free energy will change as you do switching. So, for example, at A I am in saturation polarization state, right. So, which means all the atoms are shifted at A within. So, we can say that the free energy curve will look like this. I have applied an extra electric field. So, the wells are tilted in this direction. So, all the atoms sit here. The energy to go to this direction is very high, but all of them can fall here. So, which means my energy wells are tilted extremely in this direction and all the atoms sit here. This is the situation at A. What is the situation at B? Situation at B will be like this. So, both of the wells are at equal height. So, this is B, right. When you come to C, what will happen at C? You applied an electric field, but still there are some atoms here, there are some atoms here, and both of them are equal, right, in amount. So, as a result polarization is equal to 0. When you go to D, it will all be like this. So, all the atoms come here, right. When you go to E, it again goes to a sort of equilibrium. This is like this. So, there are more atoms sitting on E than here. So, you can see that there is a minus PR. This is minus PR, this is minus PS, this is 0. So, you have all that. So, basically you can say plus PR is equal to minus PR in this case. In this case you have plus PR. Okay. So, what minus PR will mean is that your minus P is more than plus P, right. And then when you go to F again, you are applying positive field, but then your wells are becoming like this, but then you can see plus P is equal to minus P. But this is how free energy, as you apply the electric field in one direction, the wells get tilted to one direction, and when you apply very large field, they tilt in such a manner so that all the atoms hop to one direction. That is when you reach minus PS or plus PS. But when you are at 0 field, the wells are symmetric. So, but there is an uneven distribution because of switching process, and so although there is a equal probability, but because of the way switching has happened, not all the atoms of negative position move to positive position, or not all the positive atoms move to negative position atoms. Okay. So, this is how the switching happens in these materials. We will look at the microscopic aspects of switching and the free energy well and thermodynamics a little later on. Thank you.